Hi, I'm Connor DiMatteo,
I'm George Curiosas.
And I'm Caleb Morgan.
and this is the self-sustaining hydroponic greenhouse with photovoltaic power and optical sensing. We are Group 5, and our problem statement was to solve the problem of community gardens and accessibility within municipalities. So we decided to invent a automated greenhouse system that can be used in localities to create community gardens by eliminating the need for people, resources, and knowledge to grow produce within a city.
Welcome to the garden. Whether you are a home gardening enthusiast, a charitable organization, or even a municipality, this greenhouse will inspire you with its focus on sustainability and accessibility. Using a combination of commonly found building materials, pre-engineered components, and a touch of novel engineering, this community garden is well suited to function autonomously without the need for constant monitoring, resources, or even knowledge. By implementing hydroponic techniques in a vertical fashion, we've dramatically reduced the total space needed and overall water consumption. Featuring its own power generation and water collection, our system is optimized and operated with a variety of electrical and optical components, truly making this a garden of the future. We thank you for taking the time to listen as we take you through our 5 subsystems for an in-depth look at the future of sustainable agriculture in cities near you. Beginning with our power generation system, we have constructed a solar framing mounted at 30 degrees to power the garden. These two 100-watt solar panels supply power to a 12-volt DC battery with the support of a solar charge controller. We are firm believers that if this garden is ever going to be utilized in communities around Florida, then it must be able to function without the use of municipal resources, and that includes power. These panels find themselves permanently installed a short distance from the greenhouse while the battery and charge controller are located within. This charge controller regulates and monitors the power being supplied by the panels directly to the battery. The battery itself powers the PCB, DC to AC inverter, and a simple relay. The system incorporates many components, some of which either needed too much current, like the diaphragm pump, and some of which required AC power, like the ultraviolet purifier. In order to monitor and regulate our current and voltage, we also incorporated a voltage regulator rated for 12 volts and 4 amperes.
So here we're looking at our gutter water collection system. It's all being funneled into a 3D printed design that takes different mesh screens that we can easily replace. And that is to make this rainwater collection system fully self-reliant so we don't have to supplement our own water into it. So here you can see an overview of our filtering system. You can see that there's a 50 mesh right there being fed straight to our diaphragm pump. That diaphragm pump is pumping at 80 psi into our filter. And that filter has currently 4 stages of activated carbon and our UV system. And then it's all being pumped currently in this video to our Raman spectrometer. So here's our UVC filtering system. You can see our UVC bulb out of the aluminum housing, but normally we put that inside as the water is flowing through the system. By using UVC, we're purifying the water completely. This eliminates all good and bad microorganisms. However, we're introducing our own nutrients and pH after the fact, so this just ensures that we have nothing bad getting into our water. Here's an overview of our Raman spectrometer. You can see the Ocean Insights provided units, which are the Raman spectrometer and the laser, but we also had to create our own power supply for those. So that's just being run off of the computer through a modified USB cable that we created to run those. And you can also see our 3D printed housing in the back. Looking at our Raman spectrometer, we can see that it's very portable and easy to set up. Here's our lens design for the Raman spectrometer, and we have water coming after the filter, flowing through the pipe, and then to the solenoid where it's being sent to our system. You can see that the fitting is actually very easy to take off and put on, so that makes it very easy for us to place this Raman spectrometer anywhere in our system to analyze the water. So here's everything that you need to perform Raman spectroscopy. You can see our laser module here and our Raman spectrometer all being fed by these 2 fibers into our 3D printed housing for all the lenses that are analyzing the water. So using Ocean View with our Raman spectrometer, we're actually able to see our peaks And this shows us by comparing it to a known baseline of pure water that the water after the filter is pure and ready for plants to use. We're also able to prove that our laser is producing 785 nanometer light by shooting it in free space. And this shows us on the spectrometer that we successfully see a 785 nanometer spike.
Immediately following our Raman spectroscopy is our system-specific reservoir. This reservoir features a naturally circulatory design by having the right can take all water inputs and the left can pump all the water outputs. Here we demonstrate a user activating a plant profile for our system to begin self-regulation. On the blue buoy we have an optical pH sensor attached, as well as our submersible pump and an EC TDS sensor. The water level sensor rests lower in the can to detect when the water will be needed from the central reservoir. The other sensors will activate our nutrient and pH deposition system.
You can see our nutrients film technique hydroponic system here. That's all being fed by a submersible pump that's in our sub reservoir that has all of the pH and nutrients in the water. And you can see the water actually flowing underneath these plant cups, providing all the plants their nutrients and pH and water through their root system. Here we're demonstrating the water as it flows down to the second layer through gravity and then exits into our exit reservoir, which leads directly back into the sub-reservoir to be rebalanced and used again for our plants. Now, per specification, you can actually see the dimensions we decided to use to build our hydroponic systems. This actually ensures that we're able to fit 3 of these whole systems inside of our greenhouse, which is actually what we're planning to do after this to actually finish this as a community garden for the city of Oviedo.
The peristaltic pumps are capable of pumping 100 milliliters per minute of solution into the subsystem reservoir. In this video, you can see the nutrient peristaltic pump activate after the microcontroller receives a TDS level that is below the minimum required level. This pump will go for 20 seconds, resulting in about 33 milliliters of nutrient solution being added. This is the right side of the subsystem reservoir, which receives the water returning from the hydroponic system. Peristaltic pumps are also routed to this side of the reservoir, allowing for the solutions to be properly mixed prior to entering the hydroponic system. This is also beneficial for sensor readings. Here we have our PCB. On the left we have our PCB with all our components installed for a one hydroponic system setup. On the right is a rendered image of the same PCB. In this rendered image, you can see the location of the different components of the board. The 3.3 volt regulator circuit consists of noise reducing capacitors as well as a 12 volt to 3.3 volt regulator module. The liquid level sensing circuit uses 2 pin reducing multiplexers as well as pull down resistors to record liquid levels. The low side drivers enable or disable a given load. Each line can support up to 500 milliamps at 12 volts with our current setup. The additional pH and TDS sensors can be seen on the right side of the board. The microcontrollers, the MSP430 and the ESP01S, sit in the center of the PCB. Their programming pins are also located near the pH and the TDS sensors. Here we are demonstrating the boot time for the system. This was done by powering the system and seeing how long it took for the watering process to begin. This occurred almost instantly. In this video, we are demonstrating how to connect to the greenhouse website. We locate the greenhouse access point on our user device under Wi-Fi settings, then navigate to a web browser of our choosing. We type in the default gateway 192.168.4.1 into the address bar and are granted access to the greenhouse. To configure plant profiles, we navigate to the Configure page and click Edit. In this example, we have a plant profile, potato, that we want to set active on System 1. System 1 is currently active, so we must first deactivate the profile on System 1. This feature prevents the user from potentially altering a system which they do not want to alter. After performing this operation, you can see the change has been applied. Plant profiles can also be removed with a simple click of the Remove button located on the right side of each plant profile row. All plant profiles and updates to the profiles are stored in non-volatile memory on the MSP430 microcontroller to retain data in the event of power loss. The website view from a mobile device can be seen in this series of images. In this sequence, we are also demonstrating the ability for our system to self-balance to a predefined plant profile, butter lettuce. The parameters for this profile were set to a minimum TDS level of 650 ppm and pH in the range of 5.5 to 6.0 pH. This also shows the ability for our sensors to meet their specifications. In order to verify our results, we took measurements using additional handheld sensors. In this image, we can see that we are measuring a pH of 5.92, verifying our previous results.
We in Group 5 thank you again for joining us on our walk through the garden. We truly hope you enjoyed our greenhouse. As we come to a close, we are eager to see people across the globe take up the fight as we have against food insecurity as we take strides towards a brighter future.